Good day. So in this session, we're going to answer your first lecture exercise under the derivatives of single variable functions. So it's quite a number of problems that we'll have to solve today, but just hang tight since all of these problems are quite straightforward. It's very easy so long as you know the rules of differentiation. And if you're patient enough to practice taking derivatives of these simple functions that you will most likely encounter in your theory courses in the subsequent terms. Right, so let's answer the first problem, which tells us to get the derivative of the two functions that's given in the example using two different ways, using chain rule and power rule. So our first problem is we just wanted to solve for the derivative of x to the fourth raised to the fifth power, right? Now, if you're asked to get the derivative of this function using the chain rule, well, first you'll have to take the derivative of the outer function, right? So if you're asked to take the dy take the derivative of y with respect to x, so that's going to be dy over dx, all right? So that's going to be 5 x to the fourth raised to the fourth power, multiply that with the derivative of the inner function, which is 4x raised to the third power. All right, so that's 5x to the fourth, 5 times x to the fourth, x raised to the fourth power, raised to the fourth power times 4x cubed. Okay, so that's going to be 20, right? 20 x to the fourth raised to the fourth power times x cubed, right? So simply, that's just going to be 20x. So you multiply this becomes x to the 16th power times x to the third power. So that's going to be x to the 19th power. Or simply put, if you just wanted, if you want to get away with if you want to do away with using the chain rule, you can just expand the expression and turn this to x raised to the 20th power. And of course, the derivative would still be the same by using the power rule. Using the power rule, the derivative simply of dy over dx, or the derivative of y equals x raised to the 20. It's just 20 x raised to the 19th power, which is of course a rather straightforward way, and of course the answer should be the same. Okay, now let's move on to the second expression. So you have y equals 1 minus x to the 1 minus x cubed, right? Now, of course, you would argue that this is far simpler than using the chain rule, or of course, you can expand the expression. You can turn it to 1 minus 3x plus 3x squared minus x cubed, right? So in the first expression, you'll need to use the power rule. So using the power rule, you'll get dy over dx equals 3, 1 minus x squared, right? And now expanding the expression, you have 3, 1 minus 2x plus x squared, which of course translates to 3 minus 6x plus 3x squared. And of course, as expected, we should be getting the same set of answers, no? Or sorry, you have so you have 1 minus 2x, yeah, 2x plus x squared, all right? Okay. And of course, don't forget the negative sign here. So no, don't forget the negative 3 because, well, if you take the derivative of the inner function, that's going to be negative 1. So you'll have negative 3 plus 6x minus 3x squared. Now, of course, if you take the derivative of the expanded function, you should be getting the same answer. So that's dy over dx. So that's 1 will cancel out. So you're left with negative 3. You're left with 6x. And you're left with, of course, if 1 cancels out, you take the derivative of negative 3x, you get negative 3. You take the derivative of 3x squared, you get 6x. You take the derivative of negative x cubed, you'll get negative 3x squared. Right? And the answer should be the same. Right. Now, let's go move on to a rather abstract formula, a rather abstract function that you will most likely see in your macroeconomics. So suppose you have a function of y, a function of capital, right? And let's suppose that k is a function of time, right? Some macroeconomics textbooks will tell you, right, that k or capital would most likely be a function of time, right? Let's imagine that y is output, f is, and it's supposed to be a function of capital, big K, and let's suppose that capital grows over time, right? So it's a function of t. Now, what if you wanted to get the function of, or wanted to see the growth path of y with respect to time, right? So to do so, we'll need to follow chain rule, right? In essence, y now becomes a function of time, right? So y now becomes a composite function of, if you plug in k here in the production function, let's imagine that this production function, you'll get a composite function of time, right? And if you take the derivative, obviously, if you take the derivative of y with respect to t, you'll need to use the chain rule. So it's going to be the derivative of the outer function f prime of k times the derivative of capital, right? Derivative of capital. Or if you wanted to be a little more explicit, you can just say dk over dt, right? Or it's actually similar to say f prime of k, right? Times h prime of t. Interestingly, some textbooks will also use this notation. So if you see this notation later on in your macroeconomics, right, dot, you have an over dot. When you say an over dot, it's similar to taking the derivative of that variable with respect to time. So that's y dot equals f prime of k c times times its corresponding derivative times the corresponding derivative of k with respect to time, or k dot. So all of these are similar. They're analogous. So let's move on to number 3. So I'm now trying to answer number 3. Right. So you have y as a function of k. So here we're given that y should be a function of k. Okay. And k is a function of t. Right? It's kind of similar to the second problem. And we have k, let's say it's an arbitrary function of t. Right? Now we're asked to get the derivative of y. We're asked to get the derivative of y with respect to t at t equals t sub 0. So we'll just have to copy. We'll just have to copy the first formula, or in the formula in the previous problem. So dy over dt will be equal to f times k c dot h prime of t. Now we're asked to get the derivative of this at t sub 0. So instead of using an arbitrary t, it's just going to be h prime t sub 0. So that's pretty straightforward for number 3. Okay. Now for number 4, you're asked to differentiate or get the derivative of this function g of w, where w is raised to the negative fifth power. Okay. Okay, so to take the derivative of this, we can just use power rule. Pretty straightforward power rule. So g prime of w will just be negative, just negative 5 w, then negative 5 minus 1, that's going to be negative 6. Straightforward answer. Okay. Now, let's move on to the next problem. Let's move on to the next problem. Let's see. If r if r is equal to s raised to alpha, okay, and we say that s is 1 plus beta k raised to gamma, right? And k is equal to a t rho, or p, sorry, it's p plus b. Find an expression for dr over dt. Okay, so we're asked to get the derivative of r with respect to t. All right, so for an easier visualization, maybe you can just plug everything in. Right, so that's going to be r. So r is now equal to some bracketed term raised to alpha. Okay, some bracketed term raised to alpha, because s, we know s is 1 plus beta. All right, but we know that k is also a function of t, so that's gonna be beta raised to some with a parenthetical function raised to, okay, that's the thing about this software. It's difficult to work around with the formulas. Raised to gamma. Okay, that's better. So that's a t raised to p plus b gamma raised to alpha. So it's a sort of a deep chain rule that we need to do in order to extract dr over dt. So dr over dt requires some series chain rule application. So that's going to be alpha, but it should be easy, right? It's going to be this function, this inner function, right? Alpha 1 plus beta a t p, a t raised to p plus b raised to gamma. Of course, you'll raise this again to alpha minus 1. Okay. And of course, you have another inner function. I have another inner function. So that's going to be beta gamma. Okay. At raised to p. Okay, let's just type it. So at raised to p plus b raised to gamma minus 1. Okay, let's add a parenthesis here to avoid confusion. And then you'll need to take the derivative of this inner function. So that's another c dot uh, p a t raised to p minus 1. And that's simply it, right? That's the derivative of r with respect to time, right? So several application of chain rule from the outer function, and then you take the derivative of the inner function, right? So you get beta gamma, atp plus b y minus 1, gamma minus 1, and then you take the derivative of the inner function. That's going to be p at times p minus 1. Okay. All right, so that's number 5. About number 6, okay, number 6 we'll have, it's pretty simple. You just take the first order derivatives of this function. So if you have y equals negative 7e raised to x, right, exponential functions, right, dy over dx of this function will just be negative 7e x, right? Have you seen memes? No, if you have seen memes involving exponential functions, you're taking the derivative of the exponential function, nothing happens. Then this is a good application. Okay. Right. Now, next we have y equals e raised to some function, right? Some negative 3x squared. Okay. You take the derivative of this expression, you have dy over dx. So that's just negative, uh, well, application of chain rule. So you just still have e raised to negative 3x squared, right? Because nothing happens to this outer function, but you'll have to take the derivative of the embedded function in the exponential function in this exponent. So you'll get negative 3, negative 6 rather, you get negative 6x. Or simply put, you have negative 6x e raised to negative 3x squared. Okay. If you're taking up statistics now and you're asked to get the integrals of, say, exponential distribution, more or less you have encountered this already. Now, what about the combination of exponential and log function? Now, recalling our discussion in the thread, we're using log and ln interchangeably because in statistical softwares, log and ln are practically interchangeable now, right? Unless of course you specify the base. Unless of course you specify the base, if it's base 10 or not. But normally in most statistical econometric software, log is now tantamount to ln. Right. So we have two functions. You have e raised to the x and you have a log function, log x squared plus 2. So you need to use the power rule, or sorry, you need to use the product rule to get the derivative of this function. So let's start off with the first expression. So that's going to be, well, the derivative of e to the x is just e to the x. So that's e to the x times log of x squared plus 2, right? Plus, right, e to the x times the derivative of this log function. So the derivative of this log function again requires some chain rule because you need to get the derivative of the outer function first. So that's going to be 1 over x squared plus 2, and then you take the derivative of the inner function, which is basically 2 cancels out, so it just becomes 2x. Okay. So that's your derivative. You can just leave it as it is, but if you're a little bit obsessive compulsive, you can just factor out e to the x, right? And rearrange terms if you must, right? But then again, as it is, it's fine. Right, number 7. So suppose you have, let's try a new slide. Suppose you have a profit function, right? You have profit function pi. In economics, you usually use pi. For microeconomics, you use pi for profits. In macro, you use pi for inflation. Right? So you have pi of q, qp of q, and if you're already familiar, this is basically your revenue. This is your revenue, QP of Q, and then you have constant marginal cost, assumingly constant marginal cost. So you have C of Q, right? And P is a differentiable function, and C is a constant. Now we're asked to get the derivative of the profits with respect to quantity. How does profits behave with respect to quantity, given that the marginal cost is fixed and given that your demand given your price function is not constant, right? This is basically What happens if you have a monopoly, right? The firm faces the entire demand function. If you are in a competitive market, this P of Q is just constant, right? But since it's not, you'll get a condition where the marginal revenue must equal marginal cost, and that will be the profit maximum. But first, let's get the expression. Let's get the derivative of d of pi with respect to quantity. How does profit behave with respect to changes in quantity sold if you are a monopolist? Okay, so you need to use the product rule, all right? You need to use the product rule. So you have P, right? For simplicity, uh, let's just use P. Fine, let's use P of Q. Right? P of Q plus Q times P prime of Q, right? Product rule minus small c, right? Minus small c. Okay, and that's basically the formula. And for monopolists, you'd have to set this equal to 0 and then solve for Q. That will be your profit maximum, right? And that you will most likely encounter this in your micro too. Okay? But this is your basically this is your marginal revenue function. And if this is not a constant, if the cost is not a constant, if the marginal cost is not constant, we have a functional form for the cost, then you'll see that the condition should be that the marginal revenue should be equal to, you should see the condition that the marginal revenue is equal to the marginal cost. Right? So that's micro. How about a macro application in number 8? Suppose you have a standard model and a macroeconomic model. Okay. So you have y equals c plus I plus bar x minus m, and we say that the function of we say that the consumption, household consumption, is a function of income, obviously, and you'll see this in macro 1. And we also saw that imports in macro 2, of course you see this in macro 2, the function is, it's a function of income. When a country's GDP increases, you'll expect imports to increase because people have a higher purchasing power and you have higher income, right? Okay, so the question is, what would be the derivative of aggregate income with respect to with respect to a change in exogenous investment? Right? What would be dy over di? Right, now you'll have to be very careful here because you need to apply a bit of a chain rule, right? You'll have to plug in some functions. So in which case, let's try to plug in f of y in lieu of consumption. You'll have exogenous investment here. You have exogenous exports, x, and you have another function for y. Now, for simplicity, you may want to move. You may want to move all of the y functions on the right hand side. Right? You may want to move all of the y functions on the right hand side. So let's do that. So you have y minus f of y plus g of y equals I plus bar x. Of course, you'll see that x will definitely disappear. No, if we hold exports constant, right? If you hold exports constant, you can get an expression for derivative of y with respect to investment. So take the derivative of that with respect to I. So you have dy, or you have dy over di, right? Basically the derivative of the first term, minus f prime of y times dy over di plus g prime of y times d dy over di. Right? For the right-hand side, you take the derivative of I with respect to I, that's just 1. Right? X will definitely disappear because we will basically, we assume this to be exogenous. And for this application, let's assume that this is a constant. Right? It's exogenous, so you just treat it as a constant. Right now, factoring out dy, let me just copy this. Factoring out dy with respect to di, okay, you'll get bracketed term here. So you have negative f prime of y plus, sorry, you have 1 minus f prime of y plus g prime of y. Okay. Times times dy over di, and that's just equal, the right hand side is just equal to 1. Therefore, the dy over di is equal to 1 over 1 minus f of y, f prime of y plus g prime of y. Okay? So basically, you're looking at the multiplier. Right? This is basically a multiplier. 1 is the multiplier of investment. How much y increases when you increase investment by 1 unit. Right? And by assumption, we saw that, well, we didn't see, yeah, we have an assumption. F prime of y is less than 1. So this is just a fraction, right? We haven't seen an assumption for g prime of y, but supposedly if this is greater than 1, then of course this dampens the multiplier effect. Right? So if you have higher investment, but generally higher investment will lead to higher income, and normally this would be positive because f prime of y is less than 1. Okay. So that's number 8. Okay. So I'll basically just answer probably just one more problem, right, under second order derivatives. But of course, I think this should be pretty straightforward. Okay, if the function is, if the second derivative of a function is positive, then you have convex function. If it's negative, then you have a concave function. So let's try with number 2, and then you can just do the rest. So suppose you have f of x equals x squared minus 2x plus 2. Of course, the first derivative of this function will just be 2x. Right? 2x minus 2. Right? Then the second derivative, f double prime of x, would be equal to 2. Right? So this indicates that since this is positive, the original function, x squared minus 2x plus 2, is a convex function. This is basically a parabola, right? Parabola whose vertex is uh, basically below. It's a U-shaped. Function. Okay, it's a U-shaped function. All right. Now, how about number 3? Maybe you can start with number 3. Right. You have y equals alpha k of alpha, and most likely you'll see this again in macro. Right? Let's examine for concavity and convexity. Now, if you take the derivative of y with respect to k, right, you'll get what? You'll get alpha. And by assumption, we said that alpha is positive, and it's between 0 and 1. And we'll also assume that a is positive. So alpha k, alpha minus 1. All right. Now for the second derivative, d squared y over dk squared, right? You have alpha times alpha minus 1 a k raised to alpha minus 2. Okay. Now, here's the thing. Since alpha is below 1, is between 0 and 1, this term will be what? This will be negative. Alpha is positive, but this bracketed term is negative. Alpha is also positive. K is assumed to be positive. So no matter what kind of exponent you put in there, right, is going to be positive. Therefore, this entire expression will still be negative, and therefore, this production function, this seemingly this function that looks like a production function will be concave, right? And that is typical in macroeconomic. That's typical in economic theory, encountering functions that are concave because they possess the nice properties of functions of theoretical functions in economic theory that will allow us to get some optimum. Okay. So I'm leaving the rest of the exercise to you, and if you have questions, I'll be more than happy to address that in the discussion section.